Hello everybody and welcome to section 12.5. In this section we're going to be talking about functions of three input variables to kind of complement the discussion that we've been having about functions of two variables. Before we can really dive into the main topics of this section, we need to talk about a couple of surfaces that come up often. Okay, so preliminary examples A and B are going to lead us in that direction. So let's look at preliminary example A together here. They'd like us to find the equation for a sphere of radius r centered at the origin. That's a surface that's going to come up a lot. And let's start with a picture here. Okay, so we'll put the origin at the center, 0, 0, 0. Okay, and I'm going to just draw kind of an arbitrary point on the outside of the sphere, x, y, and z. And they tell us that the radius is r, so we're going to have a radius of r there. And I want to emphasize that we want to think of this xyz as being an arbitrary point. How would we come up with an equation for this surface? Well, one way to get started on it is to ask yourself, what is the key property that a sphere has? Okay, a sphere is really about distance. Every point on a sphere has a distance of r from the origin. Okay, so coming up with an equation would be describing that sentence that we just put into words. Okay, so the distance between this arbitrary point xyz and the origin has to be r. There's actually a distance formula, okay, which you've maybe seen before. So the distance between xyz and 0, 0, 0, I'm just going to write distance, has to be r. And that distance can be measured by the distance formula, which looks like this. Okay, you might remember seeing that in a geometry course or something. Okay, so what we've just written down is an equation for the sphere because it describes the property that a sphere has to have. Okay, if you take this equation and simplify it, okay, we can get rid of those zeros and just rewrite it like that. And we could even square both sides to get rid of the square root, and that turns this equation into x squared plus y squared plus z squared equals r squared. We're going to take that as our final answer. There is the equation for the sphere. You might notice it looks very similar to the equation for a circle. It's just got an extra term. Okay, and that's a formula that we'll come back to several times over the course of the semester. Okay, let's jump down to preliminary example B here. And this gives us several surfaces in three-dimensional space that they'd like us to sketch. Okay, and there's something interesting about all of these surfaces. They have something in common, and that is that they appear to be missing a variable. Okay, what do I mean by that? Well, take x squared plus y squared equals 4, for example. It doesn't have a z in it. Okay, and x squared plus z squared equals 9 doesn't have a y in it. Turns out that surfaces like that are kind of special. Okay, but before we actually try to sketch these, I want to give you an example in two-dimensional space that might help you just to grasp the concept of drawing these surfaces. Okay, so let's see if we can sneak this in up here. Okay, so think 2 dimensions now. So an x and a y-axis. What if we wanted to sketch the graph of the curve y equals 3, let's say? Okay, well, going back to algebra, you might look at that and say, oh, y equals 3. If I just plot that point on the y-axis, it would be right here. Is that the whole graph of y equals 3, though? It's not. Because of the fact that by writing y equals 3, what we're saying is all points in the xy plane where y is equal to 3. That's more than just the point that we drew here. That would be any point where y is equal to 3. So that's actually a horizontal line that we're talking about. Okay, we're going to use kind of the same principle to graph these three surfaces that we're looking at down here. So let's start with x squared plus y squared equals 4. Okay, I'm going to draw a set of axes for us here. So x, y, and z. Okay, and with all of these, we're going to use kind of a similar strategy. We'll start in 2 dimensions and ask, what would x squared plus y squared equals 4 look like in 2 dimensions, just x and y? Well, that would be a circle of radius 2. Okay, and we're going to draw it in the xy plane. By that, I mean the plane that contains the x and the y axis. Okay, so the circle is going to look like this. So 2 and 2. Okay, but then the z variable is missing. Okay, so kind of using the same idea that we did up here in 2 dimensions, we have to think about the z this way. Z can be anything because it's missing from our equation. So imagine taking that circle and extending it up and down in the z direction. That's what we mean by saying z can be anything. So this circle is going to stretch into a cylinder. Okay, if we move up and down. Okay, because of the fact that z can be anything. So there is the graph of x squared plus y squared equals 4. It's a cylinder centered along the z-axis that has a radius of 2. Okay, let's move on to the next one. X squared plus z squared equals 9. What would that be the graph of? Okay, and again, I apologize. My drawing skills are not the greatest here. Okay, well, in 2 dimensions, x squared plus z squared equals 9, that's the equation of a circle, but this time the circle is in the xz plane and has a radius of 3. Okay, so if we draw just the circle part of it, it's going to look like this. So that's a 3 and that's a 3. But because the y is missing from this formula, y can be anything. So imagine taking that circle and just extending it right and left to kind of allow for the fact that y can be anything. And notice that, again, we get a cylinder, but this time it's a cylinder that's centered along the y-axis. Okay. And finally, we come to y equals x squared. What would that look like? Okay. Again, let's draw both sides of our axes. So x, y, and z. Okay, so we're going to start in 2 dimensions with y equals x squared. What is that the graph of in 2 dimensions? That's just a parabola. Okay, and so we kind of have to, the y-axis is kind of a strange place. It's here. And so the parabola on this picture would actually look like this. It's symmetric about the y-axis. And because z is missing from our equation, we need to think of extending that parabola up and down. Okay, I'm just going to extend it up because extending it down would be kind of hard to see what we're looking at. Okay, so imagine taking every point on that parabola and extending it straight up. And so what you get is kind of a sheet, okay, that has the parabola as its base. Okay, just to emphasize what's being hidden from us, I'm going to dot one of these lines. Okay, so that's kind of hidden behind the sheet. All right. And so that's a rough sketch then of what we're looking at, the graph of y equals x squared in 3-dimensional space. This, by the way, is also called a cylinder, but it's called a parabolic cylinder that we're looking at.